Hi there. We've now finished nuclear reactions and we're moving on to our next topic in the particle and waves unit. And this next topic is called wave-particle duality. If I write stuff down on the whiteboard, I'd appreciate you get it into your red jotters. There usually would be some experimental work, or at least a demonstration of some work that I would show you in class. Obviously, that's not going to be possible, so I've got a video which will show you the experiment instead. I've got a couple of diagrams of bits of equipment. I would advise you, when I say so, when it's time, is to stop or just pause the video, this lesson video, have a look at the diagrams where necessary, have a look at the experiment video, and try and get something out of that. If you're able to, then print out the bits of equipment on the piece of paper that I've given a link to at the end. There's two bits of equipment. We'll be referring to both of them, going through how they're used. If you can print out the sheet with the two bits of equipment on, that would be helpful. If you can't, then it's possible to make a couple of diagrams yourself, and I'll be referring to the diagrams, or I'll draw a little diagram myself and you can copy it down. As you know, my diagrams aren't the best all the time, so if you can print stuff out, great. Right, so we'll crack on with this. So what is wave-particle duality? And if it's written down here, I suggest you copy it down, please. Okay, so this is when light can sometimes be considered to be a wave, and at other times light is better explained as a particle. And so we've got this thing called wave-particle duality, and dual or duo is two things. Sometimes we can think of light as a wave, sometimes it's more helpful to think of it as a particle, and it all depends under what situation, what experiment, what bit of theory you're trying to explain. And it helps to either use what's called the wave model or the particle model. So we have some ideas of what light is, but of course we can't zoom in on light to actually look at light, so we don't really know what it is. So we're not quite certain, but sometimes it's better to explain it as a wave. Sometimes it's better to explain it as a particle. So there are two theories. Now, to back up the two theories, the wave model is one theory and the particle model is another theory. To back these up, we need to have some experiments, and there are in fact some different experiments, and we'll be looking at what these are over the coming weeks. We'll be looking at what the practical experimental evidence is that shows us whether light is a wave or whether it is a particle. Now, this discussion's been going on for hundreds of years, going right back to Newton, and Newton firmly thought that light could act as a particle. But later on, and we'll see this later on in this unit, another scientist called Thomas Young in the 1800s, he showed that light was a wave. And so there was a bit of a conundrum, which is right, and it was left to Einstein to actually say, well, both theories are correct, and that sometimes it's a wave, sometimes it's a particle. So it's probably not escaped you that this unit is called particles and waves. So we're now beginning to home in on actually what the title of the unit is. Is light a wave? Is it a particle? So we've got this wave-particle duality thing. And we've got an idea that sometimes we can think of light as a particle. And other times we can think of it as a wave. So the most immediate bit of work we're going to do now is we're going to have a look and show what evidence do we have that light is actually a particle. And this is shown by something called the photoelectric effect. And we'll have a look at that. That's the bit of work we're going to start off with. Later on, once we've done this whole particle model of light, we'll move on to the wave model, and we use something called interference to show that light can be thought of as a wave. So I'd like to say that there are two learning outcomes, and if you're looking in the boat book, one of them is learning outcome 13A, and the other one is 14A. And it would be a good idea if we actually said, what are the two learning outcomes that you need to know about? And I'm going to write them down. So I'm going to rub this out. If you do need to get to the stage where you haven't caught up with me, then just pause the video. I'm going to pause myself here because I can't find my rubber. Yes, I can. Can find my rubber to rub that out. And I'm going to write down what are the two learning outcomes that we're going to be looking at. This one to start with over the next probably a couple of weeks, which will take us into, well, will take us from learning from home, remote learning, will probably overlap with the return to school, and this will definitely be done in the return to school. I don't really know much about how we're going to manage the return to school, whether you're all back, whether some people are back. There may be a little bit of mixing of these two things around somehow. Okay, so the very first learning outcome in this section we're going to look at, which is about the photoelectric effect. What you need to do is this learning outcome, plain and simple, says, know that so if you get asked a question in a test or exam or a block test, what evidence do we have for light being a particle? You can write down simply it's something called the photoelectric effect. It's just a bit of learning. Now, that's going to take, as I said, probably a couple of weeks from this lesson onwards into next week. Now 14A, which is the next section, which is the interference section, basically says exactly the same, but doesn't have photoelectric effect. It has interference, and it doesn't have the particle model. It has the wave model. So know that interference is evidence for the wave model of light. And this is another quite common question. What evidence do we have for the wave model of light? And you just say interference, and that's it. So a couple of weeks on this, probably a couple of weeks on this, and then that's 2 sections left. The wave particle duality starts off with this photoelectric effect and then carries on with this interference effect, and then there's only another couple of sections left, I think. After that, one's called spectra and the other one's called refraction of light. So we're getting near the end of this unit. Probably I'm estimating probably about 6 to 8 weeks work left tops of this stuff here for particle and waves. Right, so we're going to kick off then with the photoelectric effect. I'm going to say what that is. So if we look at this word photoelectric, the photo bit means light. Photo is a Greek word connected with light. Electric means moving electrons. So the idea of the photoelectric effect is that light can make electrons move. Now, we've only seen before how batteries, for instance, power supplies can make electrons move, but this is a little bit different. This is how does light make electrons move. So what we need to look at, simply put, is that when light shines on certain materials, so photoelectric effect, light making electrons move. Well, where are these electrons going to move from? Well, they're actually trapped inside material, and the materials that we're going to look at are conductors, because it's easier to make electrons move from a conductor. And when I say move from, I mean actually completely leave it. So what would we be looking at? We could take a piece of metal, for instance, and obviously on the microscopic scale, the piece of metal would be made up of lots of atoms, and orbiting all these atoms are electrons going round and round and round. They're so small, and in comes some light like that. And the idea is that light can actually make these electrons fly off and leave. So I don't just mean a current in the material, the electron gets ejected or emitted. Photo emission means they actually leave the material. They're emitted or ejected from the metal, not just moving around inside the metal. Okay, so how does that happen? Well, the incoming light carries some amount of energy. And what you need is enough energy to actually break an electron out from its atom and cause it to leave. And that's the whole idea of this here. Now, we already know from National 5, so National 5 revision of the electromagnetic spectrum. And you'd have to go back and try and remember this. We've got the electromagnetic spectrum, which starts down here with radio. And then we've got microwaves. Mu, W, is a symbol for microwaves. And then we'd have infrared, we'd have all the colors of the visible light spectrum, Roy-Gabiv. We'd have ultraviolet, we'd have X-rays, and last of all, we'd have gamma at the end. And what you're supposed to remember from National 5 is as we go from here and we move up here, we know that that is increasing energy. We also know that that is increasing frequency, so the frequency gets higher as we go from radio up to gamma. These are very low frequency waves. These are very high frequency waves. And you'll notice I'm going to talk about waves. Sometimes I'm going to talk about particles, and that's what this whole wave particle duality thing is, that we can use both. And at the same time, this is decreasing wavelength. And you should know that from National 5. So these have a long wavelength, and as we go up through here, the wavelength gets less and less and less. So these are three things really from National 5 that you ought to remember, is as you move up through the electromagnetic spectrum, this is increasing energy, increasing frequency, and decreasing wavelength. So we know a little bit about this as well from National 5, is that ultraviolet light, we definitely know carries more energy, because ultraviolet light, if you spend too much time out in the sun, you can get skin cancer, because the ultraviolet incoming light has got so much energy it can damage the cells. X-rays, even worse than ultraviolet light, and gamma. Not only can it damage cells, it can probably kill them straight off as well. And we know that X-rays and gamma are both used in hospitals to treat cancer. For instance, X-rays and gamma rays will kill cancerous cells. That's because they've got an awful amount of energy that they're carrying. Okay, let's move on. Now you'll notice that I have drawn this here as a blob, which is supposed to represent a particle, and attached to it is a little wave. So this is our way of drawing when we're not sure. It could be a wave, it could be a particle. So this is our incoming bit of light. And Einstein, and this is something that Einstein did, and Einstein actually got the Nobel Prize for doing all this work. Nobel Prize in 1921. A lot of people seem to think he got his Nobel Prize for special and general relativity, and also for his famous equation E=mc², but he didn't actually. He got it for this piece of work on this thing called the photoelectric effect, and it was Einstein who came up with this word that we can think of the light being a particle that moves in a wave-like manner, or a wave that sometimes can be thought as a particle, and we call this thing a photon of light. And these little photons carry energy. If you've ever watched Star Trek, you'll know that the USS Enterprise has photon torpedoes, and you fire out the torpedoes and they carry a huge amount of energy and they blast Klingons into bits. That's not in the exam, by the way. Okay. So what we can get from this is that the energy of the incoming light is related to its frequency. It's directly proportional to its frequency and inversely proportional to the wavelength. Okay, so the energy of light is linked to its frequency. and we know what its frequency is. We could look up whatever light it is. Now, when I say light, I'm going to put radio waves in as light, even though you can't see it. And I can put X-rays in. You can't see X-rays either. There's only a little tiny bit of the electromagnetic spectrum that we can actually see, and that's the visible bit, and that's a tiny bit in the middle. The radio bit going to the left and the ultraviolet bit at the right are much bigger than just the visible light bit. So I'm going to use this word light in a loose sense, as could be anything out of the electromagnetic spectrum. So we know from National 5 that as you go further to the right in the electromagnetic spectrum, the frequency increases and also the energy increases. And so energy is proportional, directly proportional to the frequency. I'll come back to the indirectly proportional to the wavelength later. Now, we can't do any sums. Physics is all about doing sums and putting numbers in here. We can't do any numbers with this proportional sign. So what we need to do is we need to get rid of somehow of the proportional sign and put an equals sign in, and we can do then some sort of sum. But we could say E is proportional to F. And you should be familiar with this, that we get rid of the proportional sign. That's not an alpha, that's a proportional sign. E then is equal to some sort of constant what's called a constant of proportionality multiplied by the frequency. So radio's got a low frequency, so it's got a low energy. And right at the other end, gamma has a very high frequency, so it's got a comparatively high energy. Radio, low frequency, leads to low energy. And at the other end, gamma has got a high frequency, therefore must have comparatively some higher amount of energy. Okay, so if we go back to our piece of metal, there's just a metal sheet, and we've got some incoming light, and the idea is we want to find out something about the light being able to knock out an electron. So it's going to come in here, our light's going to hit an electron, and then an electron is going to move, not within the sheet, but the electron can actually get ejected or emitted. Now, because the electron's tied in to the metal, it's orbiting our atom, it's not really a particularly easy thing to do. You've got to have the right amount of energy, and that suggests that if you were to zap this piece of metal with radio waves, low frequency, low energy, you probably wouldn't get to see any electrons. Not when I say see, you probably wouldn't be able to detect any electrons leaving, because the energy that radio waves carry is pretty low, and it's not enough to be able to get an electron out of there. But higher up, as you move up the electromagnetic spectrum to the right-hand side, the energy gets more, and at very high frequencies and high energy, then the incoming light carries enough energy to kick out the electron. And there must be a sort of break point, that below that break point there's no ejection of electrons. Electrons are firmly fixed, and it doesn't matter how much radio waves or microwaves you zap your piece of metal with. The electrons just can't get away. They don't have enough energy to break the bonds. This is a little bit like ionization, if you like. There must be something coming in here that can break the bonds, that can shoot the electron out. So over here we've got low energy and low frequency. And up here we've got higher, in our electromagnetic spectrum, we've got a higher energy and a high higher frequency, and there becomes a point where above a certain frequency of light, then an electron can get removed. And below that frequency, it won't get removed. There's just not enough energy to break up the electron out. And this point above which the incoming light with a high enough energy, high enough frequency can get an electron to leave. This is called the threshold frequency. And below the threshold frequency, there's no photo emission, no photoelectric effect, no electrons are freed to leave. And above a certain frequency, called the threshold frequency, then electrons can be broken out from the metal. So we need to find out, if we want to see if electrons are going to get removed from our metal, we need to find out what the threshold frequency is for that cutoff point, where below that cutoff point no electrons leave, and above that cutoff point electrons can leave. And that really depends on how tightly the electrons are bonded in. Okay. So I've sort of hinted that the whether the electron can leave, whether it can get ejected or emitted, depends on how tightly the electron's tied in and how much energy the incoming light is carrying. So we might look at the type of metal. Now, why metals? Well, metals already have electrons which are fairly free to move. We wouldn't use an insulator, and most metals are conductors. And why are they conductors? Well, not only can electrons move around inside the metal, and that's what causes an electric current, is that you can use this light effect of light shining on the metal to get the metal to actually leave the metal itself, not just flow through it, but actually to leave. So it helps usually if it's a metal, because it's a conductor, the electrons are not tied in, and there's free electrons that can escape from the metal and disappear off somewhere. So what we want to do is take some light, shine it on a piece of metal, and see whether we can detect electrons being ejected. Or, to be precise, said Einstein, an ejected electron, because Einstein actually said, well, if light travels in this thing called a photon, which is just like one particle-like wave, one photon makes one electron leave. Excuse me. So some metals have electrons that are easily moved, and you don't need much energy. Some of them you actually have the electrons are tied in much tighter. So the amount of energy So the amount of energy to eject or emit an electron is called the work function. So the work function really means how many joules do you need to get an electron out. So we now know that the electron can be ejected depending on what is the frequency of the light that comes in, and how much energy does the metal actually need to take to allow an electron to break away from its host atom and get kicked out. So if the amount of energy is less than the work function, here's the energy coming in. If this amount of energy is less than the work function, then the electron just stays there. And it's like the energy just gets bounced off and it's of no use whatsoever. If the amount of energy that comes in is big enough, and it's bigger than this thing called the work function, then the electron can get ejected. So below the work function, insufficient energy, which means no electrons ejected. Above the work function level, there is enough energy. And so electrons are ejected. So whether electrons can leave or not depends on the work function, which is connected to the type of metal and is also connected to the frequency of the light that comes in. Below the threshold frequency, not enough energy. Above the threshold frequency, then there is enough energy. Below the work function of the metal, the electrons are too tightly bound in and this energy isn't enough to eject it. Above the work function level, remember work functions measured in joules, above the work function level there is enough energy and the electrons are ejected. Okay, so we can't see these. You can't see electrons leaving. Electrons are very, very small. They're invisible things, and you can't watch them leave. We need to carry out an experiment to see whether electrons do actually escape or not. And there are two experiments that you need to know about that can detect whether electrons are moving. How do we detect if electrons are being ejected? From a metal? I said moving just then. I didn't mean moving in. I mean moving away from. They're being ejected. How do we detect if electrons are being ejected from a metal? So there are two experiments we're going to look at. And one is called an experiment using something called a gold leaf electroscope. And we have one of these in the department, and it's a fairly easy experiment to carry out, and you can actually detect, if you like, when electrons are leaving a metal by using this piece of equipment called a gold leaf electroscope. And we have one of these, as I said, in the department. The second one is we can use something called a photo tube. Now, we don't have one of these in the department, so I can't show you this even if we were there. You just have to imagine it. Well, better than imagining things, we're going to have a look at the gold leaf electroscope. I've got a picture here which I'm going to put just here, just right now, and there is a video for you to watch as well. But a gold leaf electroscope is a box. It's not a particularly big box. It's not much bigger than, say, a calculator. It's a box about the same height and width as a calculator that stands up there, and it's made of wood on the outside, and it's got a glass window so you can see what goes on inside, and it's got a window as well which stops air currents, air drafts getting inside. This is a very, very delicate piece of equipment. And the windows do two things. They enable you to see what's going on inside the box, and there's a window on the other side as well. And also they stop drafts. The gold leaf is actually a piece of metal. You can take a piece of gold. If you took a gold ring, for instance, and you hammered it, it's soft enough metal that you can actually hammer it out and make a very, very thin film of it. A bit like aluminium foil that you get on a roll that you can use for cooking or wrapping your sandwiches in. But gold leaf is many times thinner than that. But that will give you the idea. So gold leaf is just a piece of very, very thin gold bashed out. So inside this thing called the gold leaf electroscope, we've got a rod which hangs down, and the rod goes through a hole in the top of the box. And on top of the rod is a metal disc. And this is our metal that we're going to use. And we're going to shine some light onto the metal, and we're going to see how we can detect if electrons are leaving. So I've got this rod, metal disc on the top, rod that goes down through the inside of the box, and attached to the bottom of the rod or the metal stem is just a metal plate. And it's a plate, it's about the size of a small microscope slide. It's just and it's metal, and it's attached to the rod. So I've got a rod with a plate on the end, and glued on to the top of this plate is a piece of gold leaf. And the gold leaf is just glued at the top here. It's just glued at the top. So what can happen is the gold leaf can move up and down, and how it moves up and down depends on how many electrons there are in the plate and in the metal stem and in the gold leaf. And at this point, it would be a good thing to do would actually to stop this video and watch the video that shows you how this experiment is carried out. So we would take a piece of metal, perhaps not even the metal that's built in to the gold leaf electroscope, but you can take a piece of zinc metal, and you can stick your zinc piece of metal, polish it up. You need to polish it up so it's not oxidized. Zinc metal it's not rust, because rust is what you get on iron, but you get a layer of corrosion on the top, and we want to get rid of that. So you polish up your piece of zinc, stick it on the top here, so it's going to get ready to receive some light. And then you're going to take a light and you're going to shine a light on here. And the way that this works is shown in the video. That what you do is you charge up, what's called charging up, a bit like charging a capacitor. You charge up the electroscope. A couple of ways of doing this. You can either charge it up by taking literally a plastic pen on your jumper, and you can rub the pen on your jumper, and then you can bring the charged pen over to the electroscope, and you can take some of the charge on here and stick it inside the electroscope. Get the same thing with a balloon. You take a balloon, rub a balloon on your jumper, bring the charged balloon, the statically charged balloon, over to the electroscope, and you can take some of the charge off the balloon and stick it into the electroscope. And when you do that, there's charges stored up inside here, and the charges make the gold leaf go up like that. I think I'll get you to stop right now, pause this teaching video, and go and watch the video that I have put in the link, and then we'll come back. Okay, so I hope you have seen that experiment in action by looking at the gold leaf electroscope. And this is my diagram. If you couldn't get that diagram printed out, then you could just draw a picture of a gold leaf electroscope, and it's the box, and running down the inside into the inside of the box is this metal rod, and on top there we'll stick the plate on the top, and hanging from the side of the make it a bit longer. Hanging from the side of the metal rod is the gold leaf. Okay, so what we want to do is there's two charges. You know that we can get a positive charge and we can get a negative charge. This experiment only works if this metal plate and the gold leaf and the rod inside are negatively charged. Now, what does that mean? That means that there are too many electrons. So you take your balloon, you rub your balloon on your jumper, or you take the plastic rod and rub it on a piece of material, and you transfer a negative charge onto the metal plate, and the electrons that you introduce travel down the stem, and they also travel down the bit of gold leaf. And because you've got negative charges here on the stem and negative charges here on the gold leaf, this rod, which is fixed, the gold leaf can move, it can flap up and down. The gold leaf actually goes up like this, and it sticks out from the side because it's getting repelled. It's glued at the top, but it's able to freely move at the bottom, and the bit of gold leaf goes up like that. Okay, this will only work when you charge your electroscope negatively, and by charging it negatively, that means we've added in extra electrons. So it's a negatively charged gold leaf electroscope. And that gold leaf electroscope has got extra electrons. It does not work if you positively charge your gold leaf electroscope. That wasn't shown in the video anyway. But by positively charging, you take a different material rather than a balloon or a pen. I think you can do this with a glass rod instead of a plastic rod, and you can charge the electroscope up positively. Now, charging the electroscope up positively just means you subtract electrons, you take electrons out, and if you take electrons out, you get a lot of positive charge down here instead of negative charge. I'll make all this positively charged. What I've done is I've taken electrons away with my rod, and this remains positively charged. This set of positive charges repel this set of positive charges, and the electroscope goes up like that. So the whole idea of the gold leaf electroscope was invented back in the early days of electricity. It was just a charge detector, a way of detecting static electricity. It does not work, only works with our negatively charged gold leaf electroscope that has extra electrons. I've drawn that a bit too near the top of the page. I'm just going to redraw that down here. Here's my bit of metal on the top. The rod there. I've got extra electrons. I've got loads of extra electrons when I've charged up my gold leaf electroscope. I've got the gold leaf is repelled because it's also negatively charged, and so the gold leaf rises. Okay. Now, providing I've got a source of light that has enough energy, here's a source of light, and it's emitting, it's sending out light waves or light particles, as this experiment shows. The incoming particle, if it's got enough energy, that's the first thing, and if the work function of how tightly the electrons are held in here, if that's low enough, if the work function is low enough, in other words, it's easy to get electrons out, and the threshold frequency is exceeded, so that means the light has got a high enough frequency with a high enough energy. If that threshold frequency is exceeded, if the frequency of the light coming in is bigger than the threshold frequency, then as our light particle comes in here, it can cause one of these electrons to leave. Now, as more and more electrons leave, the electroscope is discharged. As you start taking out electrons, and Einstein said every one of these photons can remove an electron. So if we've got dozens and dozens of photons coming in, we're going to get dozens and dozens of these extra electrons are going to leave. And as a result, you've got less electrons down here. Less electrons means the force between the two here is not big enough to sustain the gold leaf from being held up in the air, and the gold leaf starts to fall when there's less electrons. So we can't actually see electrons leaving, but we get the idea that electrons are indeed leaving, because if they weren't leaving, the gold leaf would stay there. And the fact that electrons are being removed continuously means that there's less electrons down here. Less electrons down here repelling each other means the gold leaf then falls. So if the work function is low enough and the threshold frequency exceeded, then electrons are ejected and the gold leaf falls. So the gold leaf falling is an indication that electrons are actually being kicked out of the metal plate. Okay. In the video as well, the demonstrator used white light. And remember, white light is our Roy-Gebiv. And then the demonstrator used ultraviolet light. And somewhere between violet and ultraviolet light must be this threshold frequency. And anything below that threshold frequency, and there is a symbol for threshold frequency, F0. Anything below that threshold frequency, then electrons aren't going to leave. It's all or nothing. This is nothing. This light here has energy that's too low. The frequency is too low. The energy is too low. It's below the threshold frequency. No electrons are kicked out. Somewhere between violet and ultraviolet light, the threshold frequency is exceeded, and the ultraviolet light has a high enough frequency to actually kick out our electrons. Okay, so only electrons are ejected, and that's because our electrons can move, our positive charges can't move. Where are the positive charges? Well, the positive charges are in the middle of the atom where the protons are. So just a quick diagram of an atom. So I've got positive charges here. I've got some neutrons as well that don't count, so it's protons there, and then I've got orbiting electrons. Here's an orbiting electron going around there. Here's another one over here going around there. Okay, and it's because these electrons, these are the electrons that can get removed by the light that's shining down, has got enough energy to kick out these electrons. That's a bit like ionization, if you like. Now, you can't get protons to leave because protons and neutrons are tied together deep down into the nucleus, and it's just these electrons or the extra ones that you've put in when you charged up your gold leaf electroscope that are sort of swimming around here, not necessarily actually attached, but it's a bit like ionization, how it works. So we know that when we did ionization at National 5, that and indeed just recently at high. And we know that alpha and beta, if you can imagine that this is an alpha particle coming in here, we don't have any problem with imagining that alpha particles can cause ionization and can knock out spare electrons or weakly bound in electrons. So alpha and beta as particles can do this. So why not think of light as being a particle that can do this as well? And that's what this wave particle duality is all about, really. Okay. So that's the first experiment. Gold leaf electroscope, one photon of incoming light, one little packet of wave energy, one particle of light can remove one electron, continuously adding in more and more photons of light will cause more and more electrons to leave, and that discharges the gold leaf electroscope. Right, so the second piece of equipment is called the phototube. And again, you might like to stop here. You might like to get this picture printed out. If not, you would have to do a little sketch. And I can do a little sketch if you're not able to do printing and cutting and sticking. So what I've got is this phototube here. It's a small sealed container. So here's the container here, and I'll just draw it so that you can see what's going on. There's a container. It's a hollow container, and it's got nothing in it. It's got nothing in it. It's had all the air taken out, and it consists of a vacuum. The little container has a window, and it's a very, very thin window that you can shine light into. So you can shine your light. Just move that up a bit. You can shine your light. Here comes some light, and the light will go through the window and into the vacuum tube. Now, if light really is a particle, if you've got air particles in here, the light particle is so small that it gets affected by the air particles, and this is why it works better in a vacuum. This was exactly the same in old style TVs. Everybody has a flat screen telly these days, but if you've ever seen me use the old BBC computers in a big heavy box, that's got a big thing called a phototube in it where electrons move around inside this vacuum tube, this evacuated tube. It's got some electrical connectors inside it, so I'm going to put an electrical connector here, and I'm going to put another electrical connector here. This one is a detector connector, and this is our metal plate. This is our zinc, my metal surface here. So I'm not going to write all the labels on, but I'm just showing you how this works. So I've got two connectors, and I'm going to take a wire out, and I'm going to connect this end to the negative side of a battery, and I'm going to connect this side, the detector, onto the positive side. Okay. So this is our electron detector. So what happens here is light. I can't get this coming in, and perhaps I'll move the window down a little bit. Put the window here more. So there's the window there, and the light's going to come along like this. It's going to shine through the window, and it falls onto the metal. And if this is zinc, for instance, and this is UV light, we already know from the last experiment with the gold leaf electroscope that ultraviolet light will release an electron from the metal surface when it hits it. So in comes some UV light, bong, hits a electron which is tied into the metal, and it ejects the electron, and the electron comes shooting out. And because this side here is connected to positive, that electron is attracted towards the detector. And there's one extra thing I need to put in here, and this is an ammeter. Okay, so if ultraviolet light shines on zinc, ultraviolet light comes in, hits the zinc, ejects an electron. The electron travels easily through the vacuum, is attracted towards the positive side of this circuit, and comes around here and shows a reading on the ammeter. And so the ammeter would normally say 0, but it now says there's a current flowing. Well, what happens if this is white light? And we know that white light is made of, my pen's running out, Roiger Biv. Now remember, all these different colors, red, orange, yellow, green, blue, indigo, violet, they are too low. They're below the threshold frequency. And so if white light, any bit of white light, doesn't matter whether it's red or green or blue or whatever color it is, any bit of that light comes in here and hits the plate, it's too low a frequency, it's below the threshold frequency, and no electrons are ejected. So if there are no electrons ejected from here, there are no electrons passing over here, no electrons to complete the circuit, and the ammeter would say absolutely 0. Okay. Right. Now, if you want to see, I haven't got a video of this, but if you want to see a simulation, you should stop the video now. And stop the video now, not now immediately, but go away and have a look at one of the virtual physics simulations. Now, before I was posting up individual virtual physics simulations, and I was recording myself working the simulation sitting at home, and I put them up as a little video. You now, as of last week, you now have access to a website which has been created by a colleague of mine, and I've been helping him put this website together and get it working. And you already have the website address. I put that in an email the other day, and I think, if I remember rightly, it's called flashrepo.cyu or something like that. And there's a long, complicated password which you can put in, which I also gave you, which starts YY something or other. And you need to access that website to see a simulation of this. So go to the website. Get the password in, and you'll get then a number of options. You can select different levels, or you want higher physics, so find higher physics. And then once you get into higher physics, you'll see a number of what I call bubbles. And there's a bubble that's got ODU in it. There's a bubble that's got electro stuff in it, and there's a bubble over here, I think, which has got particle and waves. So you want to click on the particle and waves bubble. So click on particles and waves, and then you'll see a whole load of different subjects which go around. The first one we did is up here, and the last one, I think there's about 7. We did forces on charged particles, we did nuclear reactions, wave particle dualities somewhere down here. So click on wave particle duality, and then you want to have a look at the photo. Again, you get another whole series of subtopics, if you like. You need to select the one that says click on the photoelectric effect introduction. And what you should be taken to is a picture of a photo tube like that, or very, very similar, and you'll be able to have a look at what are the effects of different colored lights. And it's got a movable ammeter. You can select different colors of light. You'll have to work through the simulation. The way you do that is there's a forward click button here. There's another one down here, which is a big red button. That is a big exit button, which takes you right out of this altogether. So there's a forward button. There's also a forward right to the end button, so you can sort of jump right to the end, or you can click this repeatedly, and it takes you through the steps, and you'll see the description. So click on the forward button, and it will come up with this. It will tell you about the photo tube and how it works that I've just done. And you will have a number of different colored light buttons here. You'll have a red, a green, a blue and an ultraviolet button, and you can click on these buttons and they will simulate different colored lights coming in through here. So if you click on the red button, you'll get some red arrows, and you'll see that red, because it's below the threshold frequency, you don't get any current flowing. And green is also below the threshold frequency. Remember, I said that we've got Roy Gabiv, and then we've got ultraviolet, and the threshold frequency is somewhere between the two, and you can do red, I think you can do green, I think you can do violet, and you'll see that no current flows because the light energy is too low for red and green and violet, and indeed the other colors, and so no electrons are ejected from the surface there. And it's only when you get to click on the ultraviolet button that you can see this ammeter needle actually moves up. You're also able to change the brightness of the light, and you'll be able to see what the effect is of the brightness of the light. But I suggest you stop the video now and go off and find that, have a play with the simulation, and then come back and restart the video again. Okay, so let's assume that you're back now. And if you've done that, there were 4 buttons for colors. There was red, green, blue, I think, and then ultraviolet. That one might have been violet, I can't remember. And then there were some long buttons, and there was low brightness, medium brightness, and higher brightness. And none of these work at all. These are all below the threshold frequency. Ultraviolet does work, and then once you've selected the ultraviolet light one, you can actually see the effect on the current, on how bright the light is. Low brightness, you get a sort of small current. Medium brightness, you get a bigger current, and high brightness, you get a much bigger current. And any of these, you don't get any current at all flowing. And that shows you that if the brightness increases, the current increases, and the current is just made up of those moving electrons. Every 1 photon of ultraviolet light causes 1 electron to be ejected. If you make the light brighter, you're going to have loads of these incoming photons, and loads of these incoming photons will cause loads of electrons to leave very quickly, and more photons means more photoelectric current. So no current at all here. Yes, there is a current there, and as you go from low to medium to high brightness, then the current flow increases as more electrons are ejected. Okay, I'm now going to stop this video completely. Now we've got that far, and the next video will be how do we actually use that formula where we started off that the amount of energy is proportional to the frequency, and we can then move on, and we're going to actually do some calculations in the next video with what is the frequency, what's the amount of energy. And we'll do that next time because this video has been running long enough now. And if you've stopped and had a look at the other video of the gold leaf electroscope and the simulation of the photo tube, then that's taken you well over an hour. So I'll stop right now.